The main granddaddy reaction of carbonyl groups are nucleophilic addition reactions. Here is a carbonyl compound. If you remember, that carbon is quite a bit slightly positive, so it will react with a reagent that's got a slightly negative part, so that the slightly negative part, being a nucleophile, attacks the slightly positive carbon. And then usually we think of it that the rest of the attacking molecule, this Y here, sticks on to the oxygen. So you can think of it as indeed an addition. You've got a slightly positive carbon, slightly negative oxygen that reacts with a group that's slightly negative, slightly positive. The slightly negative part, the X, sticks on to the carbon. The slightly positive part sticks on to the oxygen. Now, for some reason, the big example that A-levels use for this is the reaction of a carbonyl compound with so-called HCN, hydrocyanic acid. So if you think about what's good about HCN, you've got a positive bit, the H plus, the CN minus, and so not surprisingly, they add on as expected. The negative CN adds on to the slightly positive carbon right there. The positive H sticks on to the slightly negative oxygen right there, giving you a so-called cyanohydrin. Now, it's possible that one of the reasons this is a very featured reaction in A-level boards is because it's easy to see the mechanism. You take your carbonyl compound, in which the carbon is slightly positive, thus attractive to a nucleophile like cyanide, Cn minus. Cn minus comes up with its electrons to the slightly positive carbon, says, "Why don't you make a bond with me?" At which point the carbon says, "Oh, I'd love to make a bond with you. I'll get rid of those pi electrons I had to the oxygen," giving them to the oxygen, putting a lone pair on the oxygen, that negative charge there. And then, of course, we have the H plus comes up part of it here. The O minus grabs onto that H plus, the O acts as a base, the HCN acting as an acid, a proton donor, or we can say that the O is acting as a base because it's an electron donor towards the H, and we make our final cyanohydrin, leaving behind Cn minus to react further. Now, a quick synthetic note about this. HCN is a terribly, terribly weak acid. So you can't just take a bottle of HCN off the shelf and stick it in with a carbonyl compound. Rather, what you do is you take a sodium or potassium cyanide in there to provide the Cn minus ions, and then you add some HCl to acidify the whole thing, thus making, in quotes, HCN, because it's really not HCN, it's Cn minus coming from sodium cyanide or potassium cyanide, and the H comes from a strong acid like HCl. But anyway, cyanohydrin, a nice example of a nucleophilic addition. The nucleophilic part, because the anion sticks on to the slightly positive carbon, leaving the oxygen to grab anything it can that's left over. Now, one reason why they do discuss this at A-levels are because cyanohydrins are actually rather useful synthetic reagents. You can make them from a carbonyl compound, and what they've done is they've allowed you to introduce an extra carbon atom into the molecule in the form of the carbon in the Cn. And something that's really important for organic synthesis is to have control on being able to add carbons or remove carbons from a structure to get from a starting material to the desired product. Okay, and so cyanohydrin, nice little intermediate molecule here in which you take a carbonyl compound, react it up with, as I said, HCN in quotes, make this cyanohydrin, and then you can do a couple of things with the cyanohydrin. You can oxidize it, and so you get rid of the N and you leave yourself with a carboxylic acid that's next to an alcohol. That's a nice little starting material or way to go a little bit further with some reactions. Or you can reduce it, throw in a whole bunch of hydrogens, and turn the CN group into CH2. NH2. So nucleophilic addition reactions exemplified first here by cyanohydrins.